Good evening, everybody. Tonight I want to talk to you about something that relates the notion of twin primes to the Euler phi function, or the Euler-Tolson function. Now, what I mean by this is that n is the product of twin primes, and so what that means is this. P is a prime, and also P plus 2 turns out to be a prime. Okay, so we'll just write it like this. A lot of people want to use P and Q. It's not really necessary right here for this particular case. Now, a concrete example would be, let's see, what do we want to try? Maybe 11 times 13. See, these two prime numbers are separated by 2, and they're both prime. So that's this form, the general form we're talking about right here. P is a prime. In this case, P would be 11. Okay. Now, notice when you add 1 to this, you get 144. Okay, but hello, that's what they call a perfect square. I just call them square integers. That's equal to 12 squared. Okay, and that's not just happenstance. We can conclusively prove this. Okay, so now just a word about this phi function. Let me just, for example, I'll just do something. I'm not going to get into a big rigorous thing about the phi function, but it's kind of a function that measures the primality of a number. Okay, so how do you make that thing properly? Does it look more like that? Yeah, okay. So phi at 11 is equal to 10. And it's a counting function. It says that all the numbers, in a way, it's the definition of a prime number, assuming you know what phi is. But all the numbers less than 11 have no common factors with 11. And you can write down the numbers 1, 2, 3, all the way to 10 have nothing in common, have no common factors. And so kind of something that's more to the point of what we're trying to do is phi of any prime. And again, if phi is defined properly, this is a definition of a prime number. Okay, composite numbers never enjoy this property. Okay, phi of any prime number is just the prime number decremented by 1. Okay, and similarly, phi at 13 would be 12. Okay, so anyway, hopefully that's enough background on the phi function and what we mean by twin primes. Now, so here's the conditions. Suppose n is the product of twin primes. Show n plus 1, and this would have been the case, n plus 1 right here, all right? And n times phi at n plus 1 are square integers, okay? Now, the very first case is very, very simple. Again, we're choosing the notation we chose a while ago. N plus 1 is equal to p times p plus 2 plus 1. And this is just, of course, p squared. And there's nothing special. The primality doesn't come into play right here. This just happens. This is a truth for any integer. So no big deal about the prime numbers on this first case. Okay, that's when you expand this out, you get this, right? You get this right here, and that's of course just p plus 1 squared. So that is a square. It's a square integer, right? P plus 1 quantity squared. And again, we did not appeal to the primality there. Okay, so we're done with this part. Okay, now let's go down and take a look at the next part. Okay. Now again, based on what I just said a moment ago, n is p times p plus 2, right? But remember, phi of p is p minus 1, but p plus 2 is also a prime, right? And it that's where the twin prime stuff comes into play. Okay. Okay. This is also a prime number, and so phi of any prime number is 1 less than the magnitude of the prime number, which is p plus 1 in this case. Okay? Now, this is kind of nice how this works out because a lot of you may recognize this. And so the primality that's all right here is the part where the primality came into play. This one, the primality meant nothing. This is true. This is true for all n, really. I mean, if you want to call it, this is true for all integers, okay? K, whatever you want to call it. Call that K. It's true for all K, a member of n, okay? But down here, we really needed to know that p plus 2 and p were prime to get these two results from the Euler phi function. Okay. Now the rest of this is very much like just a super topical problem on the internet, where the product of 4 consecutive integers plus 1 is always a perfect square. You've seen it over and over. People use large numbers, small numbers. There's probably 2,000 videos, and that's all this is. If you notice that you have p, or p minus 1 would be the first integer, p is the second integer, p plus 1 third, p plus 2 is 4. So this is a product of 4 consecutive integers plus 1. And if you've seen the proof of it, we're already done with the proof, but I'll go ahead and show you again. It turns out to be beneficial to rearrange it slightly, rearrange these factors. And that's what I did right here. Okay, and notice that and I tried to green it out so you could see that this is nothing more than a minus b times a plus b. Well, this is really the thrust of the proof. And then let's see, p plus. Oh, this should be, y'all, sorry, this should be multiplied. Sorry. Think of this as multiply, my bad. Okay. Yeah, I got that wrong, didn't I? Yeah, this should be a multiply symbol, folks. My bad. Multiply, and this is multiply right here, right? I just, for some reason, put a plus in there. So these objects are being multiplied together. My mistake. Hopefully, this straightens that out. Yeah, you can see that's supposed to be multiplication. Okay, multiplication right here. Okay, but anyway, we have the form a minus b times a plus b. Right? And you see, it's just that our a is these greened out objects, and our b is just 1. All right? So what we're going to get right here, folks, and we know that this is equal to a squared minus b squared, right? And I'm not including the 1 at this point, but a squared minus b squared. Okay. Now, so what we get right here, folks, is the following. We get p squared plus p minus 1 quantity squared. And I'm going to put minus 1 squared here just for emphasis, so you'll see. This is just how you do the difference of two squares, right? The cross terms cancel out. And then we'll go ahead and add the 1 here, which I kind of left out here, but hopefully it's not a point of confusion. And so right here, you see how cool this is. You get p squared plus p minus 1 quantity squared. Okay. And that does it. We got it written as a perfect square. Here we just wrote it as p plus 1 quantity squared for n plus 1. This was slightly more involved, but and the algebra is a little more tricky, But anyway, we got it isolated as or it's equal to a perfect square. Now I don't know if I can remember this or not, but up here, let's see, p squared plus p minus 1 quantity squared. So let's use our example right here. You would have for this part right here, you would have p. Let me just write it right underneath here. So for the case n equals to 11 times 12 right here, folks. So you would have 11 times 13. Okay. Let's see what. Well, okay. Yeah, just 11 times 13 is our n, right? All right. And then we're going to multiply it by phi of n, which is 12. And then that's going to be plus 1. Okay, and what is that? I don't even know what that's equal to. But we see that's where we can use our results, you see. It's going to be p squared plus p minus 1 quantity squared. Okay, so let me see if I can remember that. So you would have 11 squared. $11 squared plus p minus 1 squared. Oops, sorry. Yeah, no, I got it right. 11 squared plus 11. And what do we got? -1 quantity squared. Whatever that is, my friends, that's a large number that I'm not going to. So 11 squared is 121, 131. So this is equal to 131 squared. All right. But anyway, it does work out. You can verify it right over here if you want to. I think it's the same thing. But in any event, we got it. I may have made some sort of mistakes in the computations here, but we did get the job done in terms of expressing both of these objects as perfect squares. So that's all. Okay, thanks for viewing.